Hello, everyone, and welcome. It is 1 o'clock on the East Coast, and we are going to go ahead and get started with our webinar. My name is Jessica Enix, and I'm with the ACIL staff, and I would like to welcome you to today's presentation. ACIL is proud to offer this educational webinar thanks to the support of ACIL's friend sponsor, PerkinElmer. While this webinar is 100% educational, it would be amiss if we did not recognize the longtime support that PerkinElmer has offered ACIL. So thank you, PerkinElmer. Before we begin our presentation, I'd like to review a few points of protocol so that you'll get the most out of your webinar experience. Remember, you are listening to the webinar via a conference service. If you are disconnected, repeat the steps that were given to you by the ON24 registration email. In order to reduce background noise, please be aware that all participant lines are muted throughout the presentation. If you have any questions, please type them in the Q&A box on the right-hand side of your screen. All questions will be addressed at the conclusion of the presentation. Please note that today's program is being recorded. Now it is my pleasure to introduce our presenter, Ms. Lee Marotta, and supporting Lee today will be Ms. Kathleen Young. Lee Marotta started her career in gas chromatography at Exxon Corporate Research in 1988. In 1992, Lee moved on to PerkinElmer, developing methods and helping people in all industries that require gas chromatography. 10 years ago, Lee moved to a national role, focusing on the petroleum and environmental industries. With 32 years' experience in all fields of gas chromatography, Lee feels her main role is to help people be successful. Kathleen Young started her career as an environmental auditor for the U.S. Department of Energy and held environmental engineering and permitting positions at AECOM and American Electric Power. Ms. Young joined PerkinElmer in 2018 and has served in several positions related to environmental analytical field. As environmental market leader, she is responsible for the global growth strategy for penetration and expansion into the environmental testing market. She also develops actionable insights about market needs and opportunities to drive product and workflow innovation critical to this market. Ladies and gentlemen, please welcome Lee Marotta and Kathleen Young.
Thank you, Jessica, and thank you, everybody, for joining today. We would hope that this is educational for you as it is intended to be. I'm splitting this into two sections. Typically, this is a 3-part course material. So I needed to condense, because I do GC for 40 minutes, Mass Spec for 40 minutes, and then on troubleshooting and maintenance, and then columns. However, since we only have 40 minutes, I took what I felt was the most important out of those 3 presentations and condensed them. So I couldn't fit columns in, but if ACIL permits, I would love to do a column talk on troubleshooting, maintenance, and challenges with columns and selection of columns, although for most of these targets that are out, the column selection has already been done. For anything that we do, it's good to have a toolkit. I remember one time, it's Saturday, I'm heading to my lab, it's an hour away. Get to my lab, and I don't have a ferrule. I can't find the correct ferrule for the column ID I was using. So and it was a beautiful, beautiful summer day. So I was very, very annoyed. So having everything, spares of everything, will keep your laboratory moving. There's one thing that I would like to point out on this list. Well, 2 things. Detector cap or plug. These are used, the detector cap or plug is used to isolate the detector. So if there is a problem and we're troubleshooting, we like to isolate parts of the instrument to make it quicker in finding what actually the problem is. So there should be the ECD the ECD plug is different than the mass spec plug. It's just a plugging ferrule. Well, for the ECD, we use a 1/8-inch swage lock. For the mass spec, it's a 1/6-inch plug with a plugging ferrule, a ferrule that doesn't have a hole in it. So those are really important. The other thing is proper wrenches. we want to use the proper size wrench for the fitting that we need to snug. So if we're snugging the fitting at the mass spec side, which is the 16th inch fitting, we don't want to use a channel lock because we would over tighten and perhaps hurt the transfer line, but hurt the threads, but we would probably squish the ferrule. Squish is a technical term. So we want to have, and I don't like adjustable wrenches because they always move on me, so I always use fixed wrenches when I'm tightening and always have the correct size. About this, a spare source, we offer each individual part on the source as a part. So we could either have spare parts for the source, or it's very quick to just change out a source, and then you could worry about cleaning your source at a later date when there's more time. So having a spare source keeps you up and running as much as possible, I should say. Schedule preventative maintenance. And one way to do this is having a logbook and documenting every time you do something, especially if it's significant. And this also helps the service engineer, because if a service engineer comes in and sees that you may be doing something more frequently or that you did something new, it may give him or her an idea of the solution of what the problem is right now. How many times do we do preventive maintenance? Well, if we're doing drinking water, hardly ever. But life isn't that great all the time. So we do have dirty matrices in the environmental workspace. So if for instance, 8270 is going to require, because of the sample matrices, more maintenance or more preventive maintenance. But keeping a logbook gives you an idea, okay, I know I'm usually changing my liner in a month. I'm going to schedule it to be a week before that month, just so that I don't have any downtime. And I am going to discuss test mix right now, actually. Test mix are nice troubleshooting tools. Your target calibration standard test mix is really good because that's what you need to do. Internal QC and internal standard control charts, which I know everybody does, is great. Vendors also have test mix, and these test mix, we try to make a test mix that's testing the instrument and not something else that may be going on. So they're very selective, the compounds that we use to test the instruments. For instance, when we test repeatability for the liquid autosampler, we use, because we want to investigate the liquid autosampler, we're not checking for activity in the liner, so we use a very inert compound. So we get a true test of that liquid autosampler. So they're very specific. And then there's some commercially available test mix, and the Grove test mix is one that I'd like to discuss now. In the Grove test mix, this was provided, I took this from Restech's website, so I should have given them credit here. I apologize for that. They give you the chromatogram on an inert system. So this was injected in an inert system, and this is great if you're doing pesticides or 8270 with 2,4-dinitrophenol, for instance, or bases. So there's active basic compounds in this list, active acid compounds in this list, and very inert compounds like the normal hydrocarbons in this list. So if you notice that, for instance, nitroaniline is starting to fall off, well, then you know you have an active site for basic compounds somewhere in the system, and usually it's an injector port. So it's a good troubleshooting tool to say, yes, I know I have activity, that's why my recovery is low. Now, if the Grobe test is analyzed and everything looks the same, well, then there's something else causing the recovery. Usually it's activity. I find the liner is most of the problem. One time I was having a problem and I took out my liner. It looked perfect, but I changed it and my problem went away. So just inspecting the liner doesn't mean that it doesn't have something on it that's not visible to us, especially if it has a scratch in it, because a scratch, it exposes the glass that was not deactivated. So even a little scratch can cause an activity problem. Another way to test for activity, if you inject your components, do like a precision, inject your components several times. If they start to increase in intensity and then level off, that's usually indicative of an active site, because what you have been doing is with each injection, you're covering that active site until there is no more sites available for the compound to attach to. Unfortunately, that way of deactivation only lasts usually a day. But I know some of my labs that do mercaptans, they do three injections of a high standard, a blank, and then they start running their samples every day, because that's enough to and mercaptans are very active components. They stick to a lot. Okay, so now I'd like to get into the injection process. So in this section, I'll be covering the injection process, liners, and a couple of other things in the sample path from the G perspective. Okay, what are the challenges with a hot injection? You inject your nice, happy sample, and all of a sudden it gets hit with 250 to 330 degrees, and now it's not that happy anymore. Well, there's potential for thermal and catalytic breakdown. I'll get into some environmental examples later on. There's potential for backflash, syringe fractionation. Syringe fractionation is when there's too much dwell time of the needle in the injector port. What happens is if there's too much dwell time, we get discrimination favoring the low boiling point compounds. Because of the dwell time, these compounds start volatilizing out of the syringe. So what we want to do is inject as quickly as possible. So if you're with your auto sampler in the fast mode, this typically is avoided. The most of the concern is with backflash, and I'm going to get into that right away. Okay. Backflashes can result when you have vapor expansion, because you're bringing a solvent, 1 microliter of a solvent, at room temperature to a very high temperature. So you get what's called vapor expansion. And methylene chloride, water is probably the worst, but methylene chloride expands a lot as well. So that 1 microliter, and this is an example of a 2 millimeter ID volume. So that 1 microliter now expands to 400 microliters. Well, the volume of that liner is not 400 microliters. So where does our sample go? It goes outside of the liner. High boilers could condense at the top because the injector is not as hot on the top as it is in the center. It could flash back into the pneumatics, depending on how much vapor expansion, and then that's a service problem, right? Unless you change your own pneumatics. But the biggest thing is we're going to have poor precision and poor recovery. We could lose our high boilers, giving us poor recovery and discrimination across our target range. Also, we could get carryover into later injections, causing ghost peaks, because a lot of time, ghost peaks are peaks that are not nice and Gaussian because they've been hanging around. They broaden out and can interfere with your targets in the next injection. So, what are the things to consider? Well, the volume of the liner is a simple equation that we all learned back in grammar school. It's the equation for a cylinder. The other thing is cool. It's the ideal gas law. We have to consider the injector temperature will affect this, injection volume, injector pressure, and different solvents have different expansion volumes. Hexane is not as bad. There is isooctane. Ethylene chloride, again, is up there. So these are the factors to consider. So if how do we reduce this expansion if we don't have choices in changing our solvent or changing our injector temperature or changing our injection volume? A pressure pulse injection, because if we look at the equation of an ideal gas law, if we increase the pressure, we're reducing the volume. So by doing a pressure pulse injection, and in this example, we used 40 pounds, and if you're running in constant flow mode, I make that 5 mils per minute. That gives you about 40 pounds on a 30-meter 0.25 ID column. So I use 5 mils a minute, and then after a minute, I reduce my flow rate to 1 mil per minute, 2 mils per minute. I sort of program for PAHs to get those 3 guys out at the end. I usually ramp up my flow rate to 4 mils per minute before they come out to get them nice and tighter and try to tighten those guys up. I get better signal to noise that way because I get better peak efficiency. So by doing this, we're essentially eliminating our vapor expansion issues. Another way to do that is to do controlled volatilization. This is with we could do solvent purge, we could do split, we could do splitless. There's a lot of options here. But in trace level analysis, which is what we're talking about now, we're going to do a splitless injection. So we inject our sample as a liquid, and we could purge out the solvent because the injector's cold here. So we could do 50 microliters without backflash. So since the injector is cold, we're not going to get backflash. The sample is injected as a liquid and stays in the injector port, and then the solvent gradually dissipates depending upon what your initial temperature is. After we bring out the syringe, we have controlled volatilization of our targets. So this eliminates problems associated with backflash, prevents syringe fractionation, enhances recoveries, especially for our higher boiling point components, especially for thermally labeled like Endrin and DDT will definitely be enhanced using this injection process, and I have many examples of that. Could talk about that in the Q&A, or we could talk about that. You could just send me an email. Okay, now I'd like to move on to liners. The type that people have their favorite. I have my favorite. So it's whatever works for you, but there are suggestions from vendors on what liner is best for certain applications. For instance, purge and trap, you want to use, or headspace, you want to use the narrowest liner possible because the volume of the liner, even though it helps with preventing backflash, it also increases dead volume, which results in band broadening. Band broadening is bad because then you don't have as much signal to noise, you don't have as much resolution. So for For purge and trap, we use a 1 millimeter ID liner. There's special liners for pesticides. There's, in the next slide, I get into some of my favorites. Deactivation. A lot of people in the forensics industry, they do their own liner deactivation. They insert the glass well and they do 25 liners at a time. But vendors like us, like Vestec, Siltec is Vestec's proprietary. Well, they sold that, they spun that off, but that's a very good. I've had luck with that with pesticides. Very, very good. And then there's quartz liners, which are more inert than glass, but they're not as inert as the other liners. And should I use glass wool or not? Glass wool. Well, I'll talk about glass. I have a whole slide on glass wool, so let me move on. I drew these. That's why they look awful. I'm not the best artist in the world. Typically, people for splitless injections use a 2 millimeter liner, but you absolutely can use a split 4 millimeter liner in splitless mode. You cannot use a splitless without any place for the sample to mix in with a splitless liner. Split injections requires mixing. I'm not explaining this as the best as I can. I know. I'm sorry, folks. It requires some equilibration in the liner before injection. So a straight through liner will not give you precision in the split mode. So for split injections, I really like this cup liner. I found that to be the best. I put about an inch of loosely packed glass wool from the frosted area down. And for pesticides, I really like this liner. I really like this liner, but the problem is you can't put glass wool in it, and you can't really clean it because of this needle guide at the top. So it does have its little bit of disadvantages. And also, Restec also recently invented a other deactivation surface for other liners. Sorry, I don't have. We could probably spend a whole hour on injector port liners. There's many of them. The other thing some folks do, and this is a little risky because of activity. Some folks use on-column injections when they run pesticides, but then if you have very dirty samples, you're putting that non-volatile junk right onto the analytical column. Now, column vendors sell integrated guard columns, which are really, really cool because then you don't have to worry about having a butt connection where that's a source of a leak. So, but if it's drinking water running 508 or 525, those samples are clean, and we wouldn't have to clip as frequently as if we're doing dirty matrices. The other thing that's critical is the placement of the column in the injector port. Vendors do not do this to be mean. If the column is too far into that liner, the sample may not go in the column, but outside of the column, and the recovery would be poor. So the placement of the column enhances recovery. It also prevents carryover as ghost peaks, because then the targets in the next injection could get into the column and cause other issues. Cutting columns is important. The first time I installed it's snowing. The first time I installed a capillary column, I think I took 30 minutes and probably 5 pounds of sweat. Now I could probably do it in 2 seconds. but the cut should be good because you're exposing active sites and problems with transfer into the analytical column if the cut is not. I use the septum to mark. Most people use a septum. In the olden days, I used to use a Sharpie, but there's always a risk of getting the Sharpie material inside, and then you'll have contamination. Wool adds surface. It also prevents non-volatiles from clogging up the column. However, it's a great site for activities. So when we silanize ourselves, we put the glass wool in first and then silate the liner. Because then the glass wool, we cut the glass wool to insert it into the liner, sites that haven't been exposed to the deactivation fluid now have activity. That's why this is just a way of deactivating, but when the material is purchased, it comes with directions. Oh, also dirt is a great source for an active site. I found that to be. That's why preventive maintenance is really, really cool. This is just the way I change my liner. When I change it, you're supposed to use gloves, but I don't. After I insert the column, I decrease the column flow rate, increase the inlet split, bring up the temperature. I wait 10 minutes for nonpolar and 20 minutes for polar compounds to get the oxygen out before I put temperature on the column. And I'm going to send this presentation to folks, so don't worry about taking notes, writing all of this language. Septa is another cause of contamination for O-rings. For mass spec and ECD work, I found that Kel-Res off-gases the amount. Know the temperature requirements of the material because they do off-gas, and the vendor will let us know what temperature they off. I'm going to pick up this piece a little bit because we'll have many more slides in this presentation. Troubleshooting contamination. This is where isolating the parts are so helpful. Detector contamination is constant. It starts from time 0. Tap the detector, light it if it's an FID, if it's a mass spec. If the problem goes away, you right away know it's not your detector. Inlet contamination is chromatographical because usually the stuff condenses at the low temperature, and then when the void volume, after you bring up the temperature, that's when it's seen. The way I check my injector to see if it's an injector, I cool my injector, make 2 injections. Then I heat the injector up, make another injection. If it came back, then I know it's in my injector port. Solvents, an instrument blank, just hit the run button, set up an acquisition, hit the run button on the GC. If the contamination goes away, it's not an instrument problem. I've had solvents be bad. Septa on the autosampler Septa. That's why I never double dip, especially with an ECD, because ECDs pick up this. What happens is the syringe inserts that piece of Septa into the vial, and methylene chloride or hexane, it leaches out whatever is in that material and gives contamination. So people, especially with ECDs, don't double dip. What I mean is use the same vial. So if you want to do precision, you set up 6 vials instead of 6 injections in 1 vial. Gases are a source of contamination, so the tank shouldn't drop below 400 pounds. If change of tank and contamination is present, it's most likely the tank, because that's the last thing we did. Let's see, syringes could be a source. Oh, vials. Wash and waste files should be replaced. The waste file should be inspected to make sure it's as empty as possible, because that will bring contamination as well. And one time I was using an FID. I started getting contamination. My FID was crazy, and I was below 400 pounds. I said, okay, that's it. So I replaced the tank, and it didn't go away. So 2 days I spent trying to figure out what this was. The tank that I replaced it was filled with stuff, hydrocarbons. But that was that was very, very time consuming. With the column, just make sure you don't exceed the temperature that the vendor suggests. And it's recommended to not condition a column in the detector. I know sometimes there's not a choice. And clip the column if you see any non-volatile materials in that, especially if you're doing dirty matrices. I know you guys probably do that more frequently. I put this in for ECD maintenance. Tap the detector. Instead of cleaning an anode and going through that, usually if you bake the detector out, it recovers. So I tap the detector, bring up the makeup gas, wait 5 minutes to get the oxygen out, bring it up to 450 degrees. Sometimes I actually remove my analytical column and bring the oven up too to really give it a good bake. You could do it overnight, or you could just watch the millivolt reading go down on the read back. Column inspection I covered already, so I'm going to move on. Column isolation test. Is it a column problem? Well, put in a new column. If the problem goes away, we know it's the column, and it could be an older column that is still good. I usually, if I put a column back in a box, I put notes on it. Okay, I baked this to 350. This showed some siloxane peaks, so I put notes on columns that I removed from the oven. Okay, very good. So let's move on to some mass spec maintenance and troubleshooting. So here we have the system parts. We have pre-filters on our rod set so that the analytical rod set does not get contaminated. Our sauce is plug and play. It takes around less than 2 minutes to put this together and take it apart, and another 2 minutes to take it apart. All these individual pieces can be purchased. So if you, for instance, usually 2 pieces get dirty, the multiplier and the repeller, and the rest of it usually is pretty much clean. So replacing those 2 parts and then cleaning them later is probably going to keep you more productive. And it's plug and play, so there are no tools required to take it, disassemble, or reassemble. I get this question, when do I know I should clean my source? Well, if you can't get your required MDL or reporting limit anymore, that's probably time that you need to clean the source. In our mass spec, the filament current, if it goes above 3, that's indicative the source is getting dirty. Okay. I say some stuff later on in the presentation about this as well. If mass 502 intensity is getting lower, that is also indicative that the source may be getting dirty. The repeller function is there to repel the positive ions out of the source. So a clean source should show peaks with a repeller set to 0. If the multiplier voltage is being raised with the repeller at 0, this is typically needs to be raised with repeller at 0. This is typically indicative of a dirty source as well. Source cleaning, everybody has their own way. I'd rather just replace the parts that are dirty and throw them out. And typically I would just buy another source, but that's limited. That has limitations. So I just make sure my whole area is clean. For cleaning a source, I do wear gloves because your fatty acids will give you problems later on. Use tweezers when possible to pick items up instead of your hands. Powdered-free gloves or cotton gloves that won't leave fiber on the source. I like to use sandpaper. I find that's the fastest. And then I just wash the parts to get any residual material off of it. Some people like the aluminum oxide. I have a friend, he just soaks things in an acid concoction that he made up. That gets them really clean though. But that makes me paranoid. And it takes a long time. But it does make them very sparkling. And there's Dremel too. There's several ways, and I think people just have to use what they feel they like the best. Again, source contamination sources. Air is good for us, but it's not good for the mass spec. And it's not the nitrogen in the air, it's the oxygen. Oxygen is inert. Oxygen oxidizes. Remember, people go out partying on the weekend and wake up Monday morning and fill cylinders. Everybody makes mistakes. I make them every day. So we could get a bad supply of helium. Most people will use filters because this can really contaminate a system. And filters protect. I know my service engineers, they cringe if people don't use filters. So it really can save them being down from getting a bad tank. Although, they're very good. These gas manufacturers, it's very rare to get a bad tank. But it could happen. It could happen. Sample contamination can contaminate siloxanes from the column. That's why the the 5-phase is nicer than the 1-phase. The 1-phase is probably the most nonpolar column it is. 5-phase has a little bit of selectivity. It also has significantly less bleed than a 1-phase, so it's keeping your system cleaner. Phthalates from plastics. I dealt with a plastic. I contaminate my system with plasticizers. It's mass 149. Some of these contamination compounds have nice, unique masses, so I do not let anything touch plastic that I put into my system. I won't even use the squeezy bottle to fill my wash files. That's how paranoid I am. Only whatever's going in my system, it's glass, especially if I'm looking at below picogram, below sub ppb levels. I don't want to see this type of contamination. If it's not interfering with your compound, though, I understand. Who cares? But I just like to be more careful. This is just where you can see on your tuning page. Your tune page tells a lot of things about how your system is behaving. If the tuning algorithm is not running like it consistently usually does, that's indicative of a problem. The algorithm you should be getting the same numbers after the algorithm is done. Know your vacuum gauge. It tells us a lot. 1 mil per minute should give a consistent vacuum gauge all the time, value, I should say, all the time. I really watch that as well. But if these values are getting sort of wacky, that means the algorithm is not able to do its job because there's a hardware issue. It could be a dirty source. Okay, the transfer line temperature, it doesn't have to be as hot. For instance, if you're doing ECD or FID work, I'm sorry, I lost my train of thought. The norm is to be 20 degrees higher than the final oven temperature. Well, because you have a big vacuum pulling on your compounds, you don't need the sauce and the transfer line to be that hot. These are the values that I typically like when I have somebody, they're running 350 all the time with 8 mils per minute going, and that thing is a workhorse because they have very high boilers samples, so it has to meet the application. And this slide is old. I don't like to go below 240 degrees. So for BOAs, I would run at 240, the least amount. Sure. Oh, also remember the column is in your transfer line, so we don't want to exceed the stationary phase requirements on the transfer line temperature as well. Okay, let's move into the vacuum system and we'll talk about leak checking. Okay, so I don't know why I did pumping down before venting. Pumping down, your mass spec should pump down in 3 to 4 minutes, which means it's going to be returning to its original vacuum before it was vented. This is why it's also nice to know your vacuum gauge. Now, if you do this and you start pumping and it's not pumping down immediately, I mean, it should start dropping immediately. If it's not doing that, possibly, and this happened to me once, I accidentally put my source back cocked. It was crooked, so it couldn't seal, the O-ring couldn't seal. So that usually you hear. So you know it right away. The normal pressures from 1 mil per minute are less than 9 times 10 to the negative 6 torr with a 1 mil per minute flow rate. On a 2 mil per minute flow rate, it's usually 1 times 10 to the minus 5th, which is fine. That's on a 255 liter per second big turbo. If there's not a leak, so pump down, takes around 3 to 4 minutes. I usually keep the mass spec at the source at a temperature of 50 degrees while I'm doing this. I do a leak check. If my water is higher than my nitrogen, I start heating up the zones. Now the water is going to go high because you're burning off water at this point. That's fine. It's normal. And water is more difficult to pump than air, so it hangs around longer. The water's not doing the harm to your mass spec. It's the oxygen that's there. So, oxygen, a high level of oxygen, a small leak is not going to do anything, even a medium-sized leak. But if you don't see any carrier gas and all you see is air, that's a large leak. Finding leaks, the Freon spray, dust off, whatever you have, that is beautiful because it really does a good job of finding even slight leaks in a system. One time I used methylene chloride to find a leak. That was a bad idea. We don't want to use a liquid to find a leak in a mass spec. I was a newbie. So the dust off works really, really, really good. This is the way I like to see if there's a leak, how frequently. Every time I start a batch, I bring up the tune page and make sure I don't have a leak. Not after the batch, but before the batch. Water again is harder to remove. In this example, we are leak free, or we would be fish, right? Because the water is higher than the air. So this is a beautiful leak-free system. I'm in my happy place. So the first time I see a leak, the first place I check is at the connection of the mass spec transfer line. That because that Vespel graphite ferrule, my service engineers, they keep their ferrules in the GC oven just so they're always set. But when you put on a fresh ferrule and it goes through a temperature ramp, it contracts and we need to reset it. So what I usually do is I just bring up my oven temperature, bring it down, reset the ferrule. I do that twice. And usually they stay good for a month. However, it could leak, so I go right there first. And I just look at my tune page and I give it a little snug, and typically that solves my leak, is that ferrule's leaking. The septa on your GC could be leaking if you and because remember, it's unlike other detectors, the leak isn't going out, it's going into the system because you have a vacuum pulling on it. Leaks downline at the cylinder, no, they will go out. The vacuum is not a factor there. But leaks in the instrument, I would say from the injector port on, you can pick up with a leak detector because it's being pulled in. So that's why we use the dust off, because it's pulling it in. So, but remember the injector part when leak checking as well. It could be the nut on the inlet, or if you have any butt connectors, could be leaking as well. I also check, and I do this immediately. Let me go back a slide. Where is that? Okay, I'm gonna this. I turn off mass 4 and mass 18, and I look at the ratio between nitrogen and oxygen, or 28 and 32. In air, it's a 4-to-1 ratio. If oxygen is lower than 25%, when nitrogen is at 100%, that oxygen isn't coming from air. That nitrogen isn't coming from air. It's coming from somewhere else. Perhaps your helium tank has nitrogen in it. Perhaps the filters are going bad, or the leak is before the filter, or catching the oxygen, or your nitrogen purge valve, that because we can vent our mass back to UHP nitrogen instead of lab air, that valve could be leaking. So before I go crazy looking for a leak, I make sure that leak is coming from air, because it is the oxygen doing the damage, not the nitrogen. Nitrogen being around is not going to cause damage. It may change your chromatography a little bit, but it's not going to hurt anything. So you could still be productive, is what I'm getting at. So I always make sure it is air that I'm seeing. I also look at the intensity of water to 28 because, and I always know where my intensity of my helium is when I know my system is leak-free compared to nitrogen. I do that ratio too. But typically I look at 18 to 28, and 18 should be more intense. If the mass spec has been pumped and hot for a very long time, the water and may get a bit lower than the nitrogen, than the air, I should say. But don't worry, that is normal. But if it's just been pumped, the water's going to be definitely higher. Okay. Let me see if there's anything. Okay, there's nothing new. Oh, the O-ring on the inlet. Well, that's not. that's not really going to leak. But the O-ring and the O-ring on your source may be leaking. It may have gotten distorted. The inlet O-ring, usually this would not happen to, but especially if you took it out and put it back, a mistake may have happened. You could have a hair or dust on the O-ring. I know some people wipe their O-ring with methanol. I typically don't do that, but just to make sure it's got no particles on it, because it is making the seal. That's what's nice about the dust off. You could squirt it right on the side of the source and know immediately if you have a leak there. That'll let you know immediately because it's right there at the source. Venting mass spec, we want to make sure our transfer line and our source are below 100 degrees. If you vent to UHP nitrogen, you don't have to do that, so that saves you time. You could vent hot because you're not venting to oxygen, you're venting to UHP nitrogen. I always allow my turbo to reach 0 before I open up the system to atmosphere. Okay, let me move on. Okay, tuning and calibration is the last section. I like to know what the cal gas is, so because you may want to pick other fragments than the one, if you have a compound that's doesn't have any volatiles in it, you may not care about 69 and 131. So this shows you what the fragments are in the tuning material. This is typically what we tune to are these 4. Remember, tuning, well, you have to meet tuning criteria, but it's really an art. What's not an art is mass calibration. If the mass is, this isn't that bad, but if you see your mass floating, that's when you have to mass calibrate. Mass calibrate is a science. I mean, the mass is its mass. And the higher mass usually, so after we calibrate, we're in our happy place. It's sitting on, the axis is on, the peak is on, the apex is on 502. And then again, there's custom algorithms for meeting TFTPP and BFP tuning criteria. There's a custom that you could customize your peak widths and ratios if you'd like. Okay, well, guys, thanks for hanging in with me for 50 minutes. And if you have any questions, please give us a call. We're here to help. Okay, Jessica.
Thank you for your presentation, Lee. And again, if anyone has any questions, please type them in the Q&A box. We do have a couple to get us started. The first one is, how often should we tune our mass spectrometer, and how often should we mass calibrate?
I typically recommend mass calibration. You should stay, I've seen people stay stable for 5 months. 3 months definitely. And I just inspect it once a week, make sure that my peaks are on the right axis is my thing. So get in a habit of doing it either when you leave Friday night or come in Monday morning. Tuning, you do as little. So mass calibration, if it needs to be calibrated, we have to do it. One thing about mass calibrating, it won't change your ratios. So your standard calibration will still be meeting your QC. With tuning, you tune as little as you possibly can. Every time we tune, we're going to have to recalibrate our standards. So I would say tune only if you have we are having a problem. I mean, I was away from my lab for 5 months, and I came back, and my tune was bang on. I usually say, well, you have tuning criteria to meet. So if you're meeting BFB and DFTPP, I would not touch tune, only to check to make sure that you're still mass calibrated. But you could do that. You could do that by looking at your standard and seeing if the mass moved when you bring up your spectrum. Just display more than instead of displaying no decimal point in your spectrum, display 2, and you'll see right there. I just thought of that. That's silly, Lee. You'll see right there if your mass calibration is falling off. That would be easier to do. But tune, even if I was failing DFP and BFB, I would try other things before I tuned my system.
Okay, great.
Thank you for your question.
Is there a way to improve analytical performance for NGRN and DDT?
Oh, okay. Yes, I was going to discuss this. Thank you for this question. When I was discussing the cold injection, I have this customer and friend. Well, she was first my customer, and now she's my friend, at Mount Sinai Hospital in Manhattan. And she did research on the effect of DDT on breast cancer. And she ran a lot of DDT, and she would run NGRN as well, because there was a lot of spraying in the early 60s of DDT. So I said, Mary, we have this new technique. We could do large volume injection. You can increase your sensitivity of your DDT, and I think you'll get better recovery. So I visited her a month later. I said, well, how are you making out? She said, Lee, I don't need 50 microliters to get what she said, the breast tissue is loaded. I don't need that much volume. A half a microliter gives me. But the technique of injecting cold and doing a little bit of solvent purge gave her so much better recovery. She loved it. So I really recommend that way of doing pesticides, even if you don't need to do a large volume injection.
Okay.
Thank you for your question. Sorry.
I think we have time for one last question, and it is, how do you ensure BFP passes?
This is my trick. In CalGas, the ratio of mass 50 and 219, if 50 is 1.9 to 2.2% of 219, I never fail BFB. So I always look at that in my CalGas before I inject, and I always pass. So, well, thank you for that question.
Okay. I think that is all we have time for today. So again, Lee, thank you for your presentation, and thank you, PerkinElmer, for your continued support and sponsorship. And thank you all for joining us today, and we look forward to having everyone back on our next ACIL webinar.
Thank you, Jessica, and thank you, everybody. Have a great day.
Thank you. Bye-bye.